Now we'll look at a few examples of carbon-13 NMR spectra. And for ethanol here, we're looking at the carbons now, not the hydrogens. And there's only 2 carbons in this molecule, so we expect to see a pretty simple looking picture here. This signal around 50-something parts per million is associated with the carbon that's directly attached to an oxygen. We would expect that one to have a higher chemical shift than the methyl carbon that's just attached to another carbon. And so if we had other reasons to suspect we were dealing with ethanol, this would be just one more way to confirm that. We would expect to see a pretty simple looking spectrum here. If we go to something with 4 carbons, butanone, those 4 carbons are all going to give rise to different chemical shifts, just as the sets of hydrogens would give rise to different peaks in the hydrogen spectrum of this molecule. One thing about carbon-13 NMR that is different from using the hydrogen is that the peaks are not proportional to the number of carbons that give rise to the signal. So for example, this peak over here above 200, that's associated with this carbonyl carbon here, and notice how much smaller it is compared to these other 3 signals on the right. So all I'm really looking for here is the number of peaks, but their size really doesn't tell me much. Not nearly as much as what they would tell me if this was in a hydrogen spectrum where their sizes are proportional to the number of hydrogen atoms. And again, we don't see splitting patterns, we just see spikes here. But if I had, again, other information that told me I might be dealing with butanone, this spectrum certainly would confirm that, since it does only have those 4 peaks to it. Here's a molecule that, just looking at its structure, 1-chloropentane here, we would expect each of those 5 carbons to be distinct. They're all a different distance away from this chlorine on the end, and so there should be 5 signals in this spectrum, and here they are. They're all fairly close to each other, since these hydrogens are really surrounded by other the carbons are surrounded by their fellow carbons, and they all have nothing else but hydrogen in the immediate environment. We would expect them to kind of be bunched up. And again, the fact that there's 5 of them is really what we can say matches this structural formula here. We often do carbon-13 NMR on the same instrument that you would do the hydrogens, and so we're using the same sample, the same solvent. This is the deuterated chloroform that we would use as a solvent for a lot of NMR studies, and the carbon in chloroform gives a signal around 77, and it actually is split into 3 signals, and that splitting is due to that deuterium. We don't have any splitting of signals between carbon-13 and regular hydrogen, but the deuterium in this solvent does give rise to a splitting there, although it's a different kind of pattern because we're getting 3 peaks even though we only have the 1 deuterium there. And even though there's not a peak for TMS, that is our standard reference point for carbon NMR spectra. It's the carbons in the methyl groups for TMS that we are kind of using as the basis for our chemical shift scale, just as we use the hydrogens in TMS to do the proton NMR spectra. Here's an example using showing one of these benzene rings, and oftentimes the different isomers of benzene-related compounds can be compared in terms of their carbon spectra. We've got the 6 carbons in the ring that are giving rise to these 6 signals over here to the left. The methyl carbon is responsible for this peak over around chemical shift of 20 or so. And so again, the way this molecule is put together, we would certainly expect the methyl carbon to be different from the chemical shifts of the carbons in the ring, but those 6 carbons are also not equivalent. They're either going to have the OH group hanging off or the methyl, or it's going to be a carbon that is between those 2 carbons that are substituted. But even these other 3 carbons, again, their distances from the OH group, for example, are going to give them slightly different chemical shifts. And because the scale goes from 0 to over 200, that means that even if the peaks are close together, they usually are going to show up separate from one another, so that we could count carbons from the spectrum and match it up with the structure. which, by the way, I noticed this name here is not correct. In naming these, that would be the number 1 carbon, and that would be the number 3 carbon. So this is actually 3-methylphenol. But there is a 2-methylphenol and a 4-methylphenol, and their carbon signals would be different. And so we could tell apart those isomers. And benzene ring compounds show up a lot in NMR, and we're going to see them in the next unit of material as well. And so being able to interpret their spectra is a good thing to be able to do.